Hello everyone, welcome to the final lecture of week 5 of our course on AI for Earth observation. In this week, we have been primarily discussing SAR image analysis, different problems with respect to SAR image analysis, and different deep learning architectures with respect to SAR image analysis, or the architectures which are like popular with respect to SAR image analysis. Towards this, we spent some time this week discussing about object detection, which is often a popular problem in SAR image analysis. Of course, object detection also comes in like multispectral optical images as well. In the last lecture, we talked about despeckling and several other aspects with respect to SAR image analysis. We talked about, let's say, cycle GAN, knowledge distillation. We have also looked at like similar to like despeckling, which is something unique to the SAR images. We have also talked about like some other such aspects unique to SAR image analysis, such as like how to handle differences in the looking angle, or how to work with different polarization. And let's say like if we have like one polarization and not the other during the inference time. So another important aspect which in our Earth observation primarily comes when we talk about SAR images is that SAR images, they also come with the phase information, which we often ignore. However, we can account for the phase information. There are several possibilities, and one possibility is using complex deep learning. So in today's lecture, we will very briefly introduce you to the idea of the complex deep learning. So in this background, let us move ahead. So what is the motivation for the complex networks? SAR image, it also provides us with the phase information, which is often ignored in many applications or by many practitioners. Often it's ignored, like just because it's convenient to ignore. It's not because that it doesn't have important information. It actually has like really important information, but it's like often by practitioners who wants to adopt, let's say, networks straightforward from the optical images or from the computer vision domain. A practitioner just ignored more because of like convenience, right? Like because it's not convenient to make modifications to the architecture. It's like more like you have to gain some expertise, you have to spend some more time to design a specific architecture which can use the phase information, right? That's the reason like often people just ignore it. Of course, there could also be applications. I'm not denying that could also be applications where probably like phase information doesn't carry so much information. They're probably okay, you can actually ignore. But most of the applications phase actually carry important information about the target scene. So we need a mechanism to more effectively exploit the phase information or the complex SAR data. And there comes this complex deep learning. Complex networks are very naturally suited for SAR variants such as polarimetric SAR as well, and it can produce physically meaningful feature representations. So let us look at like how complex networks would work. So first, we're talking about CNNs, right? At this point, to define CNN, the first thing we need is convolution. So let us first define complex convolution. So let's say we have this complex filter matrix W is equal to A plus IB, and at the same time we have, let's say, like a complex vector H. Now with this W and H, we can simply produce the convolution of W and H as A convolve x minus B convolve y plus I B convolve x plus A convolve y. So how we are coming to this? I mean, you can just take a multiplication and we'll see like, okay, how we are coming to this particular form. So what we are saying is that, okay, inputs were complex, the filtered and the complex vector, and the output of this convolution, this is also complex. And yeah, I mean, here probably also something, a kind of form that probably you need to notice. This will give you a bit of idea like how things are working. So you see like the real term in the output, this is A convolve x, okay? So A and x, right? So from our two inputs, W and H, A and X are the real parts, minus B convolve y. So B and Y again are the imaginary parts, okay? Real, imaginary, imaginary. Whereas in the imaginary part, what we are seeing is B convolve x. So this is imaginary real, A convolve y, real imaginary, right? So in the real part, the terms we are getting are from basically real, imaginary, imaginary. Whereas in the imaginary part, as if like a cross relationship is happening. So you can also write, like this in matrix format. Now let us move beyond convolution. I mean, just convolution doesn't constitute of the CNN, right? We need like a number of other components. So how about them? Let us first look at ReLU, right? So usual ReLU, how does it look like? You just take like a given input, you just take a max of 0 at the input, right? So now, how do we really convert this to, like the complex format? We cannot just use like a max function like this, right? So there, again, there are multiple versions of ReLU that has been proposed in the context of deep complex networks. One is CReLU, okay? So which you are seeing is that it's applying the ReLU separately on the real part as well as on the imaginary part. Then another version is ZReLU, which is doing a if-else condition based on the phase of the given input. So Z is the given input, calculates its phase, and depending on what the phase value is, you either output Z itself or you output 0. So these are two variants, but there are also other variants available. Now, I will not go on discussing several other layers and all, but you can create versions of the other layers as well, such as batch normalization. Just like in the case of our usual CNN, we do weight initialization. You can do a similar thing in the case of deep complex networks as well. So we have, what we've seen is that we have different layers of the functions that form background for our, the CNNs. We have the similar counterpart functions in the case of deep complex networks as well. Now we can put them together and we can actually form deep complex network, right? So how to put them together? Here is an example use case. So given the input, let's say we are passing through complex BN, ReLU, complex convolution, ReLU, complex convolution, and then the input is added back, okay? And this gives us a residual kind of block, just as we have studied residual block in the context of CNNs. So similarly, we can design a residual block in the context of deep complex networks. We have, as you can see, we have multiple complex convolution layers in between. We have complex BN, we have the appropriate complex ReLU and all, and we have the skip connection that's adding back, right? So one question also, of course, one would ask is that, okay, we can form the architecture can we also train such networks? I mean, do we need also some kind of modification in the training process, such as the loss function and all? And the answer is yes, in the context of like loss functions and such things as well. Like there are like a counterpart. So here I'm giving just an example, that is complex average cross entropy, where what you can see again is that the cross entropy loss, this has been divided into two parts. The prediction that we are getting from the model, the real part of this, versus the ground truth that we are having. The imaginary part of this again versus the output that we are having. Okay, the ground truth that we are having. The ground truth, of course, remains the same. It doesn't vary for the real or imaginary. So that y remains the same. Compared once against the real y cap, once against the imaginary y cap. Okay. So this is one example. However, of course, like there are so many other variations that have been proposed in the literature in different contexts, right? Like in the context of classification or in the context of regression, whichever task you are handling. So this gives us like an overall idea of like how complex neural networks can be designed, and such networks are often like quite useful in the case of complex SAR inputs. So with this, we'll stop our discussion on the SAR image analysis at this point. However, we'll be keep coming back to the discussions of SAR image analysis from time to time. When we talk about change detection, let's say, we'll be talking about multi-sensor input comprising of optical and SAR. Similarly, when we talk about the applications in one of the subsequent weeks, we'll be taking examples like of SAR image inputs as well. And then again, like in the final weeks of this course, when we'll talk about foundation models and all, at that point also we will discuss how multi-sensor inputs, they play an important role in the creation of foundation models. And there we'll be discussing again SAR image analysis. So with this, let us stop here. Thank you.